All right. Welcome everyone to the seminar today. If you're watching this on YouTube but would prefer to join the seminar live, then please check the link below our video to join the mailing list. Our speaker today is Davide Gurnari, who will talk about harmonic persistent homology for disentangling multiway interactions in data. Davide, take it away.
Well, thank you very much for the introduction. Well, first of all, let me thank the organizer of this wonderful seminar series. I'm very happy that I have the opportunity to be here and tell you a bit about this work. So I'm Davide. I'm a PhD student at the Dioscuri Center in Topological Data Analysis in Warsaw. And I had the opportunity to spend the summer at IBM Research in New York. And so I will tell you about the work that I've been doing throughout the summer. And this is, joint work with, these people over here, Aldo, Filippo, Utro, Saugata, and Laxmi. So this is the plan for my talk. So I'm going to give a very brief overview to, homology. I'm sure this topic does not need an introduction in for this audience, but please allow me a couple of slides to just fix my notation also, because there is some things that are probably not extremely standard. And then I'm going to tell you something about harmonic homology and how you solve some problem in obtaining representative cycles. And then I'm going to go back to point one, because I'm going to speak about persistent homology. So once again, allow me a couple of introductory slides for that. And I'm going to then speak about harmonic persistent homology and how we can once again use harmonic persistent homology to extract real representative cycles for from our barcode or persistent diagram. Then I will briefly talk about computation, how we can compute, because we have code to compute these things from real world data. And then at the end, I will touch on some ideas about application and experiments on data from computational biology. So what's the motivation behind all of this? Well, I guess everyone here is familiar with the standard pipeline of TDA, right? We start from our data, we build a geometric structure on top of them. You choose your favorite construction for constructing a simplicial complex. You do Viettorius Rips, you do alpha, you do whatever, and then you run through it the persistent homology pipeline, and you get a barcode or a persistent diagram, right? And then if you want to use it in for some machine learning, there are different vectorization techniques, and then and there's a lot of literature on that. But sometimes you may be interested to go actually from right to left in this picture. So like if you see a specific bar in your barcode, you want to say, okay, can I actually get a representative cycles for this bar? Can I go back to my data? Because if your data points represent something of interest, I don't know, are genes or patients, maybe you want to see which data points are actually responsible for the creation of that cycle. And that's not a trivial task. So that's what we want to do. So let me just start with a couple of introductory slides, and we need to start with just our our model for representing our data, which is just an abstract simplicial complex. And this is just a slide to tell you that I'm an applied person, so everything in this talk will be finite. So I will have a finite amount of points, I have a finite amount of vertices, I will have a finite amount of simplices. And moreover, I will always assume that I have an ordering on my vertices, so I can have an ordering on my simplices. And the take-home message from this thing is just, I will denote with K subscript P, the set of p-dimensional simplices in my complex. So once I have that, clearly, the next step is I can define the p-dimensional chain group as the real value vector space generated by my p-dimensional simplices. And this is maybe the first warning. Maybe some of you are saying, oh, why are you using real coefficient? You just said that you are an applied person. Why you're not using integer mod 2? Well, stay with me for that. There will be a reason for that. Please allow me this weirdness for a moment. So we have that, and clearly the next thing that, classically we have is a boundary map, right? So for each dimension, we have our boundary map, that takes p-dimensional chains and return p-1 dimensional chains. That's great. And so, of course, now that we have a boundary map, we can define the kernel and the image of this boundary map. And so we have our p-dimensional cycles and p-dimensional boundaries, respectively. And of course, the next thing that everyone expects me to say now is we just take the quotient of the cycle with respect to the boundaries, and we get our p-dimensional homology group. So, and just notice that, my standard p-dimensional homology group will be denoted with just this H, the regular capital H, subscript P. Okay, that's great. That, classic topology. What's the thing we are going to be interested in this talk? Well, that sometimes once we have our homology group, we are, as I said, we may be interested in having a representative cycles for a given homology class. But, when dealing with, homology classes, we are dealing with equivalence classes, right? So every cycle is defined up to a boundary. So for example, here, have these two cycles that are looping around this one-dimensional hole that I have in my complex over here. And they are both representative of the same homology class, right? Because they just differ from themselves with a boundary, right? So which one should I choose? Because if I'm interested in analyzing, for example, the relationship between these vertices, because they mean something, because they're coming from some real world data, and have the feeling that these cycles might tell me something about the relationship within these vertices, which vertices should I choose? Should I choose this one or this one? So there is no unique way of choosing a representative cycle because we are dealing with equivalence classes. And this is not a new problem, right? There is lots of literature on this, and people, have been asking themselves how to choose the representative cycles in an optimal way, or what's the best way to choose a representative cycle. And for example, just, here I'm not pretending to be, to list all the possible papers, but just, have a couple of them, and this beautiful picture is taken from the first paper by Day and co-authors. And this one is from 2010. And then the second one is from, 11 years later. So there is lots of literature on this subject, especially because if you're dealing with, real world object, I don't know, meshes that describe three-dimensional object, you might be interested in finding optimal cycles or cycles that minimize the number of simplices you use. Because if you look at these things, basically everybody will agree that, the green cycles look nicer than the red ones. But this thing, once again, is not unique. What is telling you that you should take the one with the minimal number of simplices? And for example, if you look at my simple example over here, well, here you have the same amount of simplices, and minimizing the number of simplices in your representative cycle, well, sometimes will not give you a unique answer, right? And so these things usually are done in using linear programming and trying to minimize. So this is an optimization problem. We're not going to take that route. What I'm going to propose in this talk is to use something completely different. And this is where harmonic homology comes in. So let me go back to my first definition where I defined my chain group. Well, what I want to do now is to turn it into a Euclidean space by fixing an inner product. So that's why I want to use real coefficient, because I want to be able to fix an inner product. And the way I'm going to fix this inner product is just, I'm going to declare the basis of all of my p-dimensional simplices to be an orthonormal basis. So just the scalar product between two p-dimensional simplices will be 1 if they are the same simplex and 0 otherwise. So that's great because now I have a way to compute inner products. And if I have a way to compute inner products between chains, I have a way to define what it means to be orthogonal to something. And so in particular, I can define what it means to be orthogonal, for example, to the space of boundaries. And that's exactly what leads to the definition of the harmonic homology subspace, which is exactly the space of cycle intersect with the chains that are orthogonal to the boundary. So this is it was introduced in 1944 by Ekman in this paper that unfortunately for me is in German. So either if you want to read the original reference, either you understand German or you're like me, you have an office mate that speaks German, so he can read it for you. So thank you, Nicholas. But the takeaway message is that now we have a different way to define homology, and here I'm defining it with my curly H. And the cool thing about this thing is now that now in this way we are not dealing with equivalence classes anymore. Our members of this harmonic homology subspace are actual cycles, are the cycles that are orthogonal to the boundary. So now we don't have the problem with dealing with equivalence classes, because each representative here is an actual cycle. And moreover, we have this very nice result that we can actually have an isomorphism between the standard homology group and our harmonic homology subspace. And how you do that? Well, you start from just any representative of your homology class, which is just a cycle plus something in the boundary, right? Because all the representative cycles of a given homology class are same up to something in the boundary, and you project any representative cycles to the orthogonal space of the boundary. So basically, you get rid of the boundary part of this cycle. And so that's how you map from homology, from equivalence classes here to actual cycles. And just, a bit of nomenclature, the term harmonic comes from the fact that this harmonic homology group is actually equal to the kernel of this linear map that I'm sure lots of you will recognize. This is just a simplicial Laplacian. So there is being, recently a lot of literature on, this simplicial Laplacian and also the persistent Laplacian. But the thing that, that's interesting for us is that the kernel of this linear map is actually the harmonic homology subspace. And since we have this isomorphism, usually, what people know is that the kernel of this map is actually giving you the homology of the space. So, but we are not going to use this definition. This is just, for you to know where the term harmonic comes from. We are actually going to look at this interpretation, because I'm an applied person. I like to think of, okay, I have my representative cycle and I projected it to the orthogonal of the boundary. So what's nice about this thing? That if we have any representative cycles of a given homology class and we projected it to the orthogonal of the boundary, we obtain what we will call the harmonic representative. And the harmonic representative has two nice characteristics. First of all, it's unique. So no matter which representative you start from, so either, for example, if you have this hole in the bottom here, no matter if you loop it around it this way or this way over here, once you project it to the orthogonal of the boundary, in this case, the boundary is just, the boundary of this gray simplex over here, you obtain the same harmonic representative. And that's, quite intuitive if you think about it, because you remove that part of the cycle that belongs to the boundary. And moreover, you can also prove, is a one-liner proof, that this harmonic representative is the representative that has minimal norm. So it's also is satisfying some, is minimizing something. In this case, is minimizing the norm, and the norm in this case is the one given by the standard Euclidean metric that we are using. So that's great, right? Because now we have a way to associate to any homology class a unique harmonic representative. And that harmonic representative is not a equivalence class, it's a real cycle. Okay, and I have an example for you here. So let's look at, this complex in more detail. So now I have labeled my vertices, I now label my edges. And for example, as I told you, the boundary in this case is just the A plus B minus C. And here I have the signs because I need to be careful of the signs, right? Because I'm dealing with real coefficients. And if I'm using as my base for my space of one-dimensional chain just A, B, C, D, E, so this is how we can write the boundary, right? Is the space generated by this vector. And so let's look, for example, at these representative cycles, how you will intuitively maybe loop around this hole in the bottom. And then you say, well, I start from my cycle C minus D plus E, and I want to get the harmonic representative. And in order to get the harmonic representative, you just project this vector into the orthogonal complement of this space over here. So at the end, it's just linear algebra. And what you get if you do this computation, you get this cycle here. So you may be a bit upset at first and saying, well, why? I don't like this cycle. This cycle is way more complicated than this cycle I started from, right? Moreover, he has, we don't have integer coefficients anymore. But if you trust me, or if you want to try, for example, to compute the norm of this cycle here, well, you will realize that the Euclidean norm of this vector here is strictly less than the norm of this vector here. And moreover, if I were to start from another representative cycles, for example, A plus B plus E plus D, so looping around this thing, I'm guaranteeing you that you will get exactly the same harmonic representative. So in a way, the harmonic representative is unique, and so it's a natural candidate to choose if we are interested in application in which we want to go back and have actual representative of our homology class. So if there are no questions at the moment, I will introduce the next thing, which is like persistence, right? Because up to these points, we didn't have any persistence. And so I just need to have a couple of more introductory slides. So first of all, I need to have a filtration, right? So I need to have some monotonic non-decreasing function on my simplices such that it respects, phase relations. And so in a way, I can, look at the sub-level sets of this filtration function, and then I have a nested family of subcomplexes, right? So this is the standard thing. And then what we want to do is we want to look at how, homology evolves when we swipe through this filtration. And so clearly, for each dimension, we will have a sequence of homology groups, and the homomorphism between any two pairs of these groups are going to be induced from the inclusion map from Ki into Kj if I is less than j. And so that's that's standard. That's great. And so then we can finally define the p-dimensional persistent homology group as the images of this homomorphism, right? And then we will refer as the ranks of this group as the p-persistent Betti numbers. So intuitively, the p-persistent Betti numbers count how many homology classes at Ki are still present at time j. And that once that we have all of these introductory slides, then we are back at the beginning, right? We are finally back at the animation that I showed you at the start. So now we have a way to compute our barcodes, and it will be nice to have a way to compute representatives of these barcodes, right? So can we use this idea of the harmonic representative in a persistent settings? Well, the answer is yes. And actually, Basu and Cox in 2021 proved the following result, that if you look at this diagram over here, well, the top part of this diagram is just, the standard persistent homology, right? So we are going from time S to time T, and this map is just the map induced by the subcomplex inclusion. Then here at the bottom, we have the same thing, but for the harmonic homology. So what's this map strange I? Well, this map is just intuitively, how do you go from an harmonic cycle at time S to an harmonic cycle at time T? Well, when you go from S to T, your complex is getting bigger, right? So you have new stuff that appears in the boundary. So you just project the stuff that you have at time S, you project it at on the orthogonal of the boundary at time T. So this map is nothing much more than just the projection of the orthogonal of the boundary at time T restricted to the stuff that you have in your harmonic homology subspace at time S. And these vertical maps Fs are the one that I showed you earlier, that are the one that giving you the isomorphisms between the standard homology and the harmonic homology. So we are just taking any representative of a class here, and we are projecting it to the orthogonal of the boundary. So vertical thing are projection to the orthogonal of the boundary at times S, and this horizontal thing is the projection from of things at times S to the orthogonal of the boundary at time T. And the nice result is this thing commutes. So what's cool for us is that we can use any tool from the developed for standard persistent homology, pick a representative cycle, for example, the one that is given to you for free by the standard boundary matrix reduction algorithm, and just project it to the orthogonal of the boundary, and you obtain an harmonic representative. So you don't need to invent a new toolkit to deal with harmonic persistent homology. You can just use all the tools that are available for the standard persistent homology, and then just project to the orthogonal of the boundary, assuming that your tool, of course, computes homology with real coefficient. And so we can define the harmonic persistent homology subspace in a similar fashion as the standard persistent homology, just as the image of these maps, strange I. And what's nice, once again, is that this subspace is a subspace that is made of real world cycles. So we are still dealing with we can go back to our complex and look at them. You are not dealing with equivalence classes. Moreover, there is a nice result in this paper that deals with the concept of essential simplices. So before you start reading this definition, let me just give you an idea of what being an essential simplex means. So a simplex is essential for a given cycle if you remove that simplex, you don't have a cycle anymore. Or if you think about all the possible ways in which you can loop around your hole, you need to pass through that simplex. So that's what being essential means. So a simplex is essential for a given cycle. If you remove it, you cannot close the cycle anymore. And so for a given representative of a cycle, or in this case, I'm using B to denote a bar, because at the end of the day, I want to look at harmonic representative of a bar in my barcode. For a given representative, I will denote the essential content of this representative as just the sum of the squares of the coefficients of its essential simplices versus just the sum of all of its coefficients, which is basically the Euclidean norm of this cycle. So basically, this ratio is telling you how many essential simplices you have in these particular cycles relative to all the simplices that are in your cycle. And Basu and Cox, in the same paper as before, they proved that the harmonic representative maximized this relative essential content. So this is another cool stuff about your harmonic representative that is motivating why you should choose it, because it's it's basically picking the representative cycles that has the most essential simplices in it. And if you think about it, it makes sense, because I told you that the harmonic representative minimizes the norm, and here at the bottom you have the norm. So it's a bit technical, but you can prove that the fact that the harmonic representative maximizes the relative essential content is equivalent to say that the harmonic representative minimizes the norm. And an intuition for that is you have the norm here at the denominator. So if you minimize the norm, you maximize the essential content. Okay, if you are confused by this, I still have an example on this. So let's go back to our example as before, and let's try to compute the essential content of different cycles. So for example, this first cycle is the one that loops around the this hole in the bottom, and its essential cycle is 2/3, because E and D are essential. If you delete them, you don't have a cycle anymore, while C is not essential, because you can avoid passing through C by going through A and B, right? So here you have 2 essential cycles and 1 non-essential cycle, so 2/3. Similarly, if you loop around this hole by going through A, B, E, and D, so this route over here, you only have E and D that are essential, and A and B are not, because you have the options of passing through C, and so the essential content is 1/2. While if you trust me and compute the essential content from this ugly cycle that it's the harmonic representative, well, the essential content in this case is higher. And so this is telling you why this thing works. But if you don't trust me, well, this is a very simple example. So you could cook up a generic combination of looping around this bottom triangle X times and looping about around the top triangle Y times, and you can actually compute the essential context for this generic combination, and then you try to maximize this thing, or you just plug it into Wolfram Alpha if you're lazy, and you will figure out that actually the thing that maximizes that you need to loop around the bottom triangle 3 times more than you loop around the top triangle, which is exactly what the harmonic representative is doing. So this is giving you another, like a concrete example on the fact that harmonic representative maximizes the essential content. Okay, so how do we compute these harmonic representatives so what's our pipeline? Well, let's suppose that we have our persistent barcode. So you have you utilize whatever toolkit that you want that gives you a persistent barcode. And let's assume that from the persistent barcode, you can extract any representative of that bar. And you can just do it with the standard boundary matrix reduction algorithm, because that gives you representative cycles. The thing that you have to do is to compute now an orthonormal basis for the p boundary of your simplex at time birth of that bar. And once you have this orthonormal basis, now that we know how to compute scalar products and project stuff, you just project your representative of that bar to the space to the orthogonal complement of the boundary. So this is a way you can do it, and you should be done, right? Well, not exactly, because there is one more thing to take into account, that if you have bars that overlap, so if you have homology classes that are alive at the same time, in order for all of these harmonic construction to make sense, you want to also ensure that your harmonic representative that you are computing now is orthogonal to harmonic representative that are still alive at that point. So not only you have to project it to the orthogonal of the boundary, you also have to project it to the orthogonal of any other harmonic representative which is still alive. And that's a bit technical in order to assure that, that's basically uniqueness of this representative. Okay, and I guess it's time for a more, exciting example. And this is, now we have more points. And so now our one-dimensional diagram is a bit more complicated. So let's assume that we want to get an harmonic representative of this red bar here. So we look and the subcomplex at the birth of this bar is this guy over here. And a representative cycle is this red cycle here. And so now we have to do exactly what I just described. So we need to get the boundary of the complex at this time. We need to compute a basis for, its orthogonal complement. And then we need to project this cycle into the orthogonal of the boundary. And we get this thing. So this is the harmonic representative of this cycle. And maybe let's just notice that here we have a bar that is born like right before this red bar here, but it's still alive, right? So we also need to project this the harmonic representative to the orthogonal space generated by the harmonic representative of this other bar. And you can see it here, right? Because these, the harmonic representative basically diffuse over your complex. So this looks way more complicated than this. And by the way, the width of the edges correspond to the absolute value of the coefficient. But for example, you can see that, you don't pass through this edge. And why is that? Because that edge is essential for the other class, for this class that, describe this small hole over here. And, it's a bit technical, but since, essential simplices don't get touched when you project them to the orthogonal of the boundary, this simplex over here has to be, your harmonic representative has to be orthogonal to this simplex over here. So that's why you don't pass through this thing. Okay. So if there are no questions, I guess in my remaining time, I will briefly discuss some real-world example. So our focus is on application in computational biology. So, high-dimensional data coming, for example, from gene expression and stuff like that. So we built what we call our harmonic homology pipeline that works like this. So let's suppose that you have your high-dimensional, possibly multi-omics data. So you can be dealing with, genome, but transcriptome, but also, protein expression, or you can also combine all of them together. You build your simplified complex of choice using some suitable similarity measures. So depending on what you're dealing with, Euclidean metric or, the correlation between these high-dimensional vectors. And then you compute standard persistent homology. You get a barcode. And then for each bar in that barcode, you can compute the harmonic representative. And for example, if you're looking at a one-dimensional bar, what the harmonic representative is going to give you are weights over the edges, right? Because those are the coefficients in your harmonic representative. So you can extract what we call the harmonic weights for, either all the bars or a subset of bars, maybe just the longest ones. Or if you are interested in the nodes, because the nodes in this case, they may be patients or, different genes, you can diffuse these weights over the vertices. So you just, for each vertex, you take the sum of all the weights of its edges. And then you have a way to have features, harmonic features over your data points, and then you can run different type of machine learning pipelines for do classification or subtyping or biomarker discoveries. So I have a couple of examples. A very simple one is when we took gene expression data coming from breast cancer samples of different subtypes. So, and for example, LUM-A and basal are two different subtypes of breast cancer. And then you can compute the your persistent barcodes and then get the harmonic representative of these long bars over here in red. And then you look at, since each node in this dataset are like, it's a sample, and so it can be a luminal A or a basal sample, you can look at the distribution of the harmonic weights for different types of edges, because an edge can connect a luminal A with a luminal A, a basal with a basal, or two different samples of different types. And you can see that, we get exactly what we expect because we used a correlation-based matrix, and so the correlation between samples of different subtype is way lower than the what we have from samples of the same type. So the harmonic here just returns what we expect. But maybe something more interesting is when we looked at a combination of the same RNA expression data plus methylation expression data. And here I have this matrix that shows you the weights, the harmonic weights diffused on the edges this time. So we are diffusing the weights on the nodes. So each node represents a different breast cancer samples for lots of bars. So in this case, we are considering 60 different bars in our barcode. And then you can run clustering on this thing. So if we run clustering, hierarchical clustering, we see that these subset of bars have very similar harmonic weights, and they correlate very well with a specific subtype of breast cancer. In this case, I think it's basal. And so, all of these features over here with different colors are not seen, when we are building our Vittori complex. And so they think that just our harmonic weights are able to detect features in our data set. Okay, so I guess my time is almost over. So what's next? So one cool thing we are thinking about doing is to analyze the evolution of this harmonic representative. And what I mean by analyzing the evolution of the harmonic representative? Well, at this moment, I'm projecting, my representative cycles at the time of birth of my bar, right? But I could also track the evolution of this harmonic representative throughout, my filtration. And this is what I mean, right? So this is the harmonic representative of this feature evolving as I progress to my filtration. And of course, when the hole gets filled in, the harmonic representative dies because, my homology classes dies. And also you can see how they interact with other feature that, this orange feature that's born and dies in the meantime. So this is a thing that we are thinking of. How can we have all of the information about the whole life of our feature expressed throughout the evolution of, the coefficient of the harmonic representative? One other thing we are doing is to keep exploring this connection between the harmonic representative and the essential simplices, and because we know that the harmonic representative maximizes the essential content, but what can we say about that? Can we have more results? So we have some work on that. And then, of course, we are exploring more machine learning pipelines. So we have this way of extracting harmonic weights, harmonic feature from our data. What's the best way of inputting these to a generic machine learning pipeline? So how can we use this to build more features that are not coming from the persistent diagram, the persistent barcode, but from the persistent barcode, you go back to your data, you get weights on your data points, and then you use them to do your machine learning task. So I will stop here. Thank you very much for your attention. And here are the references. So, the paper by Saugata and Nathaniel, where they introduced this harmonic persistent homology concept, and our preprint where we actually compute it and apply it to different biological data set. All of the pictures that I showed you are generated through with our code that is available at IBM's GitHub. So you can recreate all of them, and you can actually play with your data and compute harmonic representative. And that's my mail if you want to drop me a line and ask me questions.
Thank you very much. That was also perfectly on time. Let's all unmute and clap briefly. Right. Do we have any questions for the public session? I didn't see anything in the chat except Niklas saying that you're very welcome for the translation. So that's good. While we are waiting for those, maybe one that would interest me, since you're dealing with single cell data or with gene expressions as well, how easy would it be to extend this to other metrics or even dissimilarity measures? Because that's what also some people are using in that realm, right? Because of the high dimensionality and these sort of issues.
Yeah, well, that's what we were using in this case. So here with this Vietnamese complex has been built using correlation distance between the gene expression profile.
Ah, okay, perfect.
Yeah. So basically, if any metrics, any way that you have to build up your simplicial complex works, because up to here, the pipeline is the standard persistent homology pipeline.
Yeah, and this I understand. Yeah.
So that's cool, because you can use all of the tools you have, in your bag, and then once you have some software that returns you, a persistent barcode and gives you any representative cycle, then you can compute the harmonic representative.
Mm-hmm. But I guess I was wondering about this representative. I should have phrased this question a little bit better. So is this with respect to the original similarities that I have, or how do I have to think about these harmonic representatives? So in which type of geometry are they living?
Yeah. So that's a way to think about it. If you use correlation, then probably this cycle over here is telling you something about genes that or samples, depending on whether you're using the matrix or the transpose of the gene expression matrix, that are highly correlated between them.
I see. Okay, that's
really
cool.
The idea. Then you go back to a subset of your genes and you look at those that are responsible for creating those features.
Very nice. So also I mean, you already have this on the side here, but so then I guess are there any strict requirements for the similarity measure that we're using? Because that's, as you said, right, you can use anything that you can calculate persistent homology of, but I was kind of wondering whether the results, are there any stronger things we can say if it's a metric, let's say stability, for instance?
I don't think so. I have to mention, I didn't have on my slides, but there is a stability result on the paper by Basu and Cox. So if you're interested for this harmonic persistent homology, I did not touch on that, but maybe it was something that it was worth mentioning, right? You can prove some stabilities from.
I see. Very interesting. We have one question in the chat, but I'm also happy to hand over to Pierrick. If you're there, if you want to ask the question yourself, please feel free to unmute.
Slide 20.
Yes, sure. I think on slide 20, can you hear me?
Yes.
Yes, and slide 20 on the right, I think I see edges on the right that enclose the smallest circle. Isn't it an essential simplex?
So I guess the resting will pass through the essential simplex on the smallest. So it does not pass through this hole. And that's the thing. So I should go back to this exactly to this example, but that's you know, the fact that let me rephrase it. The fact that you don't see the harmonic representative passing through this simplex over here is explained by the fact that you had to also project this harmonic representative to the harmonic representative coming from this bar over here. And this is why you don't see it passing through here, because you also have to enforce that your harmonic representative cycle is orthogonal to any other harmonic representative cycles that's still alive at that point. I guess that's
okay, but isn't the situation similar for the edges
on
the right?
Here, yeah, that's what I was telling, that, you know, that's, I need to check that, but probably, you know, because I'm sorry, I don't have a picture for the harmonic representative of the other bar. But I'm sure that, you know, if I were to compute the harmonic representative of the other bar, then you superimpose them and you see that they are orthogonal to each other. But it's not that. Probably the orthogonality between them is a bit more complicated than just, oh, you don't have this edge, you don't have that edge.
Okay, thanks.
Okay, no, but thank you for calling me out on that.
I have a couple of other questions. Unfortunately, I have to admit, I didn't see who raised their hand first. It somehow didn't appear on my screen. I just saw them now. So I would just call you in the order in which you appear on my screen. So please, Bei, do you want to start?
Sorry, I also have the question of the exactly same slide. My understanding is that when you actually take the generator on the left and project in this orthogonal fashion, it looks like almost every single edges has obtained some coefficient, meaning that it appear in this harmonic representation, except for the one essential edge. And then there's this dangly edge on the side, which is in some sense like extremely non-essential. Could you see something about, is this a general behavior of what I just stated?
So the way I think about it is that, you know, this harmonic representative, basically you take your your cycle here and you diffuse it along, because the thing is, if you can loop, if you have like, it's taking all the possible paths, right? Because like instead here you're forced to go through this edge because this is essential, but then it's, you know, it spreads out. And this is also like, at least for me, it's very interesting, because if you're into Hodge theory, for example, you know that, you know, if you have any you can decompose a flow on your simplicial complex in, its curl, its gradient, its harmonic component. So this is actually like an harmonic flow. Like if you look at how how the weights, for example, of these edges relates to the weights of the outgoing edges for a specific nodes, like the flow through each node is 0, right? You have no, and then since it's harmonic, the circuitation around each around this hole is non-zero, but the circuitation around each boundary element is 0. So you can, I'm not an expert on Hodge theory, but you can make sense of how, these coefficients are distributed in terms of that. And my interest lies on, relating these coefficient to the fact that of essential simplices. So one result that we have is if you look at the harmonic representative, the simplices that have the highest coefficients in the harmonic representative are the essential ones. And because those are the ones that do not get touched by this projection, because the essential simplices are already in the orthogonal of the boundary. Because they cannot, essential means that you have to pass through that edge. And, you can reformulate it by saying that you cannot there is no boundary element that allows you to, find an alternative route instead of passing through that edge. And so that essential simplices really live on the orthogonal on the boundary. So when you project them, they don't get touched by this projection. While every other simplices that has is not essential, its coefficient gets lowered by this projection because it's a projection, right?
Mm-hmm. But so except for the edge A, which is influenced by the other bar, so that's
exactly. Yes.
But my question is for B, right? B is not influenced by the other bar either, and it doesn't show up in the diffusion process either. So that's sort of
because if you think about it, if you're looping, right? If you're looping around this hole and you want to visit this, very far node here, you have to go there and then come back.
Right, but the say that C, if you look at B versus C, C is this tiny edge. C somehow got
C. There are two edges on C.
Oh, there's two edges. Okay, that resolved my confusion. Okay, all right, thank you.
You're welcome. Thank you. I just I like pictures, but sometimes I should have had more pictures because apparently everyone likes this.
Yeah, I like them. So next, I think, would be Ben, at least according to my scheme. Again, didn't see the hands go up, but we're coming to you as well, Vincent. You're still muted, Ben.
Sorry, thank you. I was curious if you had any comment on the computational efficiency of the changes that you've made in addition to persistent homology.
Yeah, so I still have one. Okay. So I have some comments on step 2, maybe. And so this thing, requires, so you have your boundary matrix, you have to compute an orthonormal basis for it. And then you need to project this thing. And, if you try to do it, for example, with just standard Gram-Schmidt, Gram-Schmidt is unstable. And so, especially if you have very large boundary matrices, then at some point you end up with garbage because numerical errors keeps accumulating. So yes, we have some tricks that you can use the fact that when you're computing persistent homology in the standard way with your boundary matrix reduction algorithm, you're doing already most of the normalization. So you can just go there and plug the nice reduced version of the boundary matrix for your purpose. But that's another interesting thing to do. If there are nicer way to store this boundary matrix, for example, or to for example, when you're proceeding to your filtration, you're adding another boundary element. You have to update your orthonormal basis, right? So it's more efficient to just, start from a small orthonormal basis and keep adding stuff, or just, look at the end of your filtration and compute it all at once. So I'm playing with that thing, but I don't have a precise answer at the moment. It's still in.
Thank you.
Thank you.
Right now handing over to Vincent.
Yeah, first of all, thank you very much for your talk. I think that's a really cool concept, and but maybe we just head over back to slide 20 because that's one with a picture. Wait, yeah, great. Okay, and now I'm asking again regarding the harmonic representative. We see that in the areas of a point cloud where there are a lot of points, or maybe where there may be more samples or something, the harmonic representative has really small values, whereas in the areas of the point cloud where there are very few samples, you get these really, really large representatives. Is this a feature? Is this something that you really actively look for in your data set, or is this something that maybe might need correction later on?
No. Well, thank you for the question. I think it's important, right? Because it relates to what I was mentioning before, to the essentialness of your, in this case, edges, right? Because if you don't have a lot of points like here, you have to pass through that edge in order to close the cycle, right? While here, you have way more routes in a way. So that's and I think that's a feature, because it's telling you something that at the moment of creation of this cycle, for example, like you will have like if your filtration is nice enough in the sense that you're adding only one simplex at each filtration step, like you will have one essential simplex. I don't know, this one gets added last, and so you will have that. But then that's also relates to the thing that was mentioning at the end, right? I will also would like to look at how these coefficients change throughout the life of this feature. Like is this last thing over here, right? Because the more stuff you add, the more possible routes you have. And so things that are essential then at some point stop being essential because a new route appears. So I think that's a feature, and also it's a result that we have that relates the weights of the simplices to the fact that they are essential or not. But also I think it will be very cool to take the full persistence into account. So see how these coefficients for different simplices changes as you go through the life of this feature. I hope.
Okay, yeah, cool. Thank you for your answer. Maybe if I just can I just ask a quick follow-up question?
Yeah, please.
Yeah, sure. Then I mean that's really cool. And then you said and it's even useful for distinguishing like concept types. But do you have any intuition why different concept types should care about like how essential some edges between some data points are? I mean, it could be the case that really in a certain area we just have a lower sample resolution. That's why these things are have a higher harmonic weight. I mean, maybe it's a tricky question. I have to admit that, but I'm really curious myself. So that's
so that was more of a sanity check for us. And so the thing is that here.
Okay, then maybe the other real world data set.
Okay. I mean, the way I see it is so first of all, here you are aggregating, you are not looking at the weight of a single simplex, you are aggregating of different types. And so I think that if you start from some sort of correlation, some similarity measure, it makes sense that you have more edges for stuff that are highly correlated. And then when you start looking at the whole bars in your barcode, not a single feature, then you start, I mean, this looks right to me, but that's also, you're right, like that was the last point in my to-do list, right? Is like to figure out what's the way to actually use these harmonics weight in the right sense for if you want to do classification, because that's the power of these two, right? Because allows you to go back to your data points in a way that's arguably canonical, right? Unique, because you have only one way to do that, to compute these harmonic weights, and so they should tell you something about your data.
Okay, yeah, cool. Thank you for the answer. And yeah, it's maybe
more than happy to to discuss it further and talk about it, because you are like, now we have this tool that allows you to compute this weight, and now you have to use it. And so that's then there is the whole interpretation, especially when you're doing with biological. I'm not an expert on that, so the whole interpretation of your findings in a biological setting, that's really complicated.
Nice. Thank you very much, everyone, for participating. We are approaching the hour mark now. In fact, we've already passed it. So I'm going to stop the recording here.